Deal. Well, let's go ahead and get started. I see Jennifer's here too. We are jamming. Hi, Jen.
I guess real quick, did I miss any like major announcements?
I just put them on the video. I was just telling them I did make the final exam practice final last night or this morning. I can't remember. One class I made last night, and the other one I had to finish this morning. So that's up. I did tell everybody that I'm trying to go through 28, 29, and 30. And my ideal goal is I will do a series of individual videos, and I have no longer till Sunday to do it. So basically, I can do today, which I did a couple, but they were 241. I can do tomorrow, I can do Saturday, I can do Sunday, but then nothing else after that is going to apply to you guys. So what I'm going to do is I'll pay attention to my dashboard, and if it looks like most of my students are actually paying attention and watching the videos that I produced and maybe even finishing the homework at least for chapters 28 and 29, then I might not even include questions from that on the final. So
Okay.
final will ostensibly be up through 30, but I might actually leave off questions from 29, 30, and maybe even 28. Okay.
Okay, so we're not going to have a third test in between now and then.
There is a face-to-face test, and I might be making an online test, but I'm going to drop the two lowest. So if you end up not getting to do it, that's fine. I know some students actually derive a good deal of confidence and happiness from having an online test on the material that we're getting ready to test for. So I probably will make another one, and just like I'll throw it up like this weekend and say you have until Sunday of next weekend, but it'll be completely consistent with you practicing for the final anyway. So if you want to do it, you
Okay.
can. If you can't do it, that'll be fine too.
That's from 24 to 25 or
Well, we already have the
or
online test
25 and
that's due to,
26.
yeah, remember we have an online test that's due tomorrow.
Yes.
Yeah, tomorrow. So it's at least two chapters after that. It might be three, but I think it's at least the two chapters after that.
Okay. All right.
Right.
Thanks.
How about
And
you,
then,
Jen? You got any questions?
yes, I was trying to do the face-to-face test, but I didn't quite understand. Are you available in person tomorrow, or is that only a Zoom thing and you're only available in person on Monday? And I'm
That would
about
be
the
Monday and
face-to-face.
Wednesday. I'm available on campus, but if you need it, I might be able to figure out a way to monitor via Zoom. Uh, I've done that before with students, but we'd have to have like a mirror or something like that. But as long as you can do that, that's not a problem. I can proctor test that way too.
I don't like that. No.
That's no problem. Well, I will be there all those hours Monday, all those
Monday.
hours Wednesday
All
as
right.
well.
Because then I gotta do, because isn't there two face-to-face next week then?
One is called a face-to-face test, but yeah, there are two tests that will be proctored. So one's a face-to-face test on Monday. The final exam could be Wednesday, but you're also allowed to take it Monday if you'd prefer.
I thought Monday was like grades due end of semester.
No, May 5th is. So that's the last day, but it has to be, if you take it on the May 5th, you'll need to be finished before 2 p.m. That's all.
So Monday is May 5th.
Yeah, not this Monday, but the Monday after is the last day you can take the final.
All right, so then I can do Monday and Monday, or I could do,
Monday and Wednesday or Wednesday and Monday. Well, you
but
can't do
Monday is the
Wednesday and
last
Monday.
day for face to face, correct?
Yes,
And
yes,
then
that's correct.
thereafter is all the final.
Exactly. But you're
Okay.
online, actually, as far as your online goes, the face to face, you have to check what I put for the deadline on that. I think it is Monday, but I might have given you more time since you are online. I'm not certain on that one.
According to your email, I think you changed it to next Friday.
Yeah, that's what I was thinking I might have did. So yeah, you have the face to face. You can take it any time between actually between tomorrow and Friday. Thanks for letting me know that, Matt. I was trying to
Okay.
remember what I said.
And we can set that up as proctored through like the testing center, right?
Exactly. Yep.
Okay.
Okie dokie.
All right.
That's what I was
All
trying
right.
to straighten out.
All right. I'm not
Thank
going to
So,
you.
trying to do it, but I'm getting ready to show you the world's or the physics 242's hardest physics problem. So, hey, y'all ready for it?
let's go.
All right, so this is the law of Biot-Savart. I'm going to write it down, and I write it down in a different format than your textbook does, but it's just like the way I did with my electric field. I ended up creating a vector that points to the point at which you wish to know the magnetic field, and I call that vector R sub P, meaning R sub point. And then I subtract from that vector R sub DL, which is sort of like R sub dq that we had in the electric field. It's the vector that points from the origin of your coordinate system to the individual piece of the wire that you say is causing the magnetic field. So I'm going to write that down and then we're going to work with it. I left myself 2 pages in case we need it, but it's pretty straightforward. It's detailed and scary, okay, but it's not that hard. All right, so let me go ahead and share my iPad screen with you guys. Is the law of Biot-Savart. I'm going to write down solution. And the solution that we're going to do will require the law of Biot-Savart. And the law of Biot-Savart says dB, a differential bit of magnetic field, remember B is what we use for the symbol for the magnetic field, is equal to mu 0 I over 4 pi times dl cross, and here's the vector that I made up, rp minus rdl over magnitude rp minus rdl cubed. So that's the law of Biot-Savart. You can see it's a little scary. It definitely has a cross product in it. In addition to that, it has a two vectors you got to subtract. But if you just go piece by piece with these formulas and a lot of stuff in physics and chemistry and engineering, it's really not that bad if you just do it. So what I'm going to do is I'm going to choose a little segment of this wire over here because it says an electric current creates a magnetic field, or all electric currents all electric current creates a magnetic field. Use the Biot-Savart law to calculate the magnetic field a distance r away from an infinitely long straight wire carrying a current I. I'll reiterate to you guys in the physics world, in the physical science world, really, if we say something's infinitely large, it doesn't really have to be infinitely large. It only really needs to be a bare minimum of about 10 times bigger than any of the dimensions that you're dealing with. So as long as the end of the wire is at least a multiple of 10 times farther away than you are from any particular spot you want to calculate the magnetic field, then it should be fine. Uh, Another thing, when you're choosing these things to do this, like in this case, this is literally a derivation. When you're doing it, I highly recommend, if at all possible, you keep it in the first quadrant or any kind of differential mass elements or anything you got to hypothesize or put in the coordinate system. Keep it in the first coordinate or on the x-axis or on the positive y-axis, one of the three. So what I'm going to do is I'm going to imagine that current I, you see its I is red and it's going upward. So I'm going to make the vector dl, and the vector dl should lie along the current carrying wire and point in the direction that conventional current's going. So what I'm going to do is make a little purple vector, and that little purple vector is going to be my dl. And its length, of course, is something I'm imagining is a differential length. And it happens to be a differential length along the y-axis. So anybody want to guess what the length of that vector is? D, let's say dy. Okay, so it's just natural if you put it along the y-axis and it's something that's straight, you should just call it dy. If you put it along the x-axis and it's something that's straight, you call it dx. If it points in the positive x direction, then it becomes dx I hat. If it points in the negative direction, it'd be negative dx I hat, or the positive y direction be positive dy j hat, or in the negative y be negative dy j hat. So that's sort of the pattern here. We're also, now that I have that vector dl up there, I've got to write out what dl is. So I'm going to say dl is equal to dy j hat. So I now have that vector. Now remember, the vector RP is a vector that points from the origin to the point P at which we wish to know the magnetic field. So I'm going to use a green vector to represent R DL and RP. So this right here will actually be my vector RP. So that vector is RP because it points from the origin to the location of the point at which we wish to know the magnetic field. Anybody want to take a poke at what that RP should be? Recall,
We're talking about the dx direction.
yeah, like the vector points to the right, and its length appears to be the little r value there. So, what do you think the vector would be?
It, um, p hat.
Uh,
Oh, well, that's what it's equal to. Sorry.
gotcha. Yeah, they got.
D. Sorry.
Well, do you know what the length is? Either anybody?
It's r.
Okay, so the length is going to be r. Now, if you had a unit vector pointing in the right direction, all you have to do is multiply the r by it.
Oh, I hat.
There you go.
Yeah.
So we're going to
So
call this r I hat. Make sense?
yeah.
Now that we have that, why don't you guys come up with on your own? You don't have to say it out, but you can if you want. For this vector RDL, which is shown right here, that's the vector RDL. Anybody want to make a guess at what RDL is? Now, this one's a little trickier because I didn't state a distance, right? But it is along a particular coordinate axis. So we often use the variable of the coordinate axis to indicate the position of something lying on the coordinate axis. So that would tell you you probably want to, and you might have already thought of this already, you would want to make it y j hat. J hat because that points in the positive y direction, and y is the variable that points from the origin. That's the length from the origin to the bottom of that little DL vector. And not only that, we have to go from y equals negative infinity to y equals positive infinity. So by using y, that automatically takes into account the negatives and the positives when I do my range limits of integration. So now I have the three vectors involved, but I need to do RP minus RDL. So now I'm going to write that down as well. So RP minus RDL is just going to be that first vector, which would be R I hat, minus that second vector, which would be Y J hat. I think I started writing a dot product there for some reason. I don't even know why that happened. Ooh. And my little eraser's become small. I don't know what that is either. All right, one last thing. We need the magnitude of RP minus RDL. And notice, by the way, RP minus RDL is really this vector. Let's see if I can draw it fairly neatly. It's this vector right here. Pointing from the bottom of DL to the point P. So that's RP minus RDL, and I think from that lets you know exactly what the magnitude is. So the magnitude of RP minus RDL is actually equal to the square root of R squared plus Y squared. So we now have all the parts to fill out the law of Biot-Savart. So now we just have to compute it, and I'll show you a nice little way of doing the cross product where you can just use the distributive property, and then all you need to know is that I hat cross J hat, or I hat cross K hat, or J hat cross K hat. Anytime you cross one Cartesian unit vector with another, you're going to get a third unit vector from third Cartesian unit vector with a plus or minus sign. Okay. If you happen to, of course, do I hat cross I hat or J hat cross J hat or K hat cross K hat, you're going to get zero. But in all the other cases, you're either going to get I hat or negative I hat, J hat or negative J hat, K hat or negative K hat. And I'll show you that as we go. So let's go ahead and begin. I'm going to switch back to my blue pen for my solution. The magnetic field B is equal to the integral of dB, which is mu 0 I over 4 pi times the integral of dl, which we said was dyj hat. That's going to be crossed with rp minus rdl, which is r I hat minus y j hat, and then all of that will be over r squared plus y squared to the 3/2 power. Remember, that's cubed, uh, but it's a cube of a square root, so that's why it's 3/2. And the reason it's cubed, of course, is ideally you just like to have the unit vector equivalent of RP minus RDL, and then it would be a 1 over R squared law, just like Newton's law of gravity and Coulomb's law of electric field or Coulomb's law of force. But because we didn't compute it as a unit vector, we have to add another magnitude down at the bottom to make it a unit vector. So that's why the 3 is there, just like the electric field was. Now that we have that, we can go ahead and start to compute stuff. Actually, instead of continuing as an equals there, what I'm going to do is go ahead and compute what dyj hat cross ri minus yj hat is. So we'll do that calculation real quick, and then I'll go back to the integral. I'm going to say dyj hat crossed with r I hat minus y j hat is just going to be sort of like FOIL method, except we're doing it with a cross product instead of just a regular multiplication. And not only that, the cross product, like the dot product, is a linear operator, which means when a linear operator acts on a collection of stuff that's like sums of scalars multiplied by vectors, you can pull all the scalars out in front and just let the vectors operate on the vectors, and any sums and subtractions and stuff like that can just be broken up as separate ones. So in this case, what I'm going to do is just take the r and the dy, and I'm going to put them out in front, and then I'm going to say j hat cross I hat. So this is where that part I was telling you about, it turns out if you take a cross product of I hat with J hat or I hat with K hat or J hat with K hat, you're always going to get plus or minus I hat, plus or minus J hat, plus or minus K hat. And there's really some nice patterns that will just automatically get stuck in your head and make it really easy. So that might help you as well seeing it. Now we've done that first term, and I'm going to work out what that cross product is in a second, but right now I want to continue on. So now I'm going to do the distributive property with dy j hat crossed with the other term. The other term is a negative y j hat. So again, I'm going to pull all the non-vector stuff out in front. So I'm going to get negative y dy. Now this time it's j hat cross j hat. So we already warned you about what that would be, but you can tell, for instance, by the formula for the magnitude of a cross product. Remember, cross product A cross B, its magnitude is given by the magnitude of A times the magnitude of B times the sine of the angle between them. If you have a j hat cross j hat, then this automatically becomes 1, because the magnitude of any hat vector is 1, times 1 for the other hat vector, times the sine of 0 degrees, and therefore we get 0. So, and that's always true. Whenever two vectors are parallel or 180 degrees apart, anti-parallel, then automatically the cross product is going to be 0. Now, regarding the J hat cross I hat, all you really need to do to work out such cross products is you just need a right hand coordinate system. And that's part of the reason why I've been telling you to make sure you always stick to a right-handed coordinate system. So you hold your right hand up, and then your index finger pointing straight ahead like this is the X direction. Your middle finger, which is perpendicular to both your thumb and your index finger, is the J hat vector, or the Y, for instance, axis, and then the thumb is the Z, the positive Z direction. So when I do that, I can just say automatically that my X is this way, my Y is this way, and my Z is this way. And then you can do J hat cross I hat. So that means use your right hand rule again. The J hat's the first one. So you're going to take your index finger and point it to the right in the Y direction. And then you got to orient your hand so that your middle finger can point in the direction of the I hat. Well, the I hat is coming out of the board. So I've got to turn my hand from this position all the way to that position. Now you see that my middle finger is pointing out of the page, which is exactly what I hat's doing. And you see that my thumb, which is the answer for the cross product, is pointing down. That's a negative K hat. So we can automatically tell ourselves that this quantity, J hat cross I hat, is negative K hat. So that's the beauty of doing this distributive property with a cross product. You only have to do I hats cross J hats or I hats cross K hats. And then all the ones that are duplicates, like I hat cross I hat or J hat cross J hat or K hat cross K hat, are all going to be zero. So what I have now is the numerator of the integrand is just going to be negative R dy K hat. So that's what's in the top of the cross product. And now you've learned yet another way of computing a cross product. So hopefully that's helpful as well. So now I can go back to B, which is equal to that integral. So we already had a mu 0 I over 4 pi. Then we had the integral, which is technically right now is going to be from uh, y approaching negative infinity to y approaching infinity. But the top part we know is negative r dy k hat. And then the denominator is going to be r squared plus y squared to the 3 halves. So we have that pretty well. I can pull, since the r is a constant and the negative is a constant, I can pull that out in front, and I'm going to get negative mu 0 I times r over 4 pi. And not only that, the beautiful thing about I hat, J hat, and K hat is you don't have to integrate or differentiate them. So you can always pull them out in front as well. And that's what I'm going to do here. I'm putting the K hat right there. By the way, notice the way I have my X and Y. Can you guys figure out on this coordinate system where I have my X, positive X axis to the right, my positive Y axis up? Can y'all see which direction K hat is? Or can you tell me whether Z points out of the board or into the board?
Well, it's heading out of the board.
Exactly. So when this thing says negative J hat or negative K hat for the direction, that means right now we're picking the direction of the magnetic field to point into the page, and that's exactly what we learned with our right hand rule. If I take my right thumb and stick it up in the direction of the red current, my fingers curl around it like this in a counterclockwise way as seen from above. And counterclockwise means that when it's to the left of the wire, it'd be pointing out of the page. When it's between me and the wire, it'll be pointing to the right. When it's to the right of the wire, it'll be pointing into the page. And when the wire is between me and the point, it'll be pointing to the left, back behind the page. So that's completely consistent with our right hand rule. that we have been learning. So now that I have that, I can now try to compute the integral. And the integral is actually one integral that we've done multiple times. It's going to be dy. Well, I've got it on automatically draw nicely, and it does not like letters when it's trying to automatically draw nicely. So all I have is a numerator. Dang it, it's still doing it. I just took it off of that. So we have a dy in the numerator, and we have a r squared plus y squared to the 3/2 in the denominator. And what we're going to do is make a trig substitution. I'm going to say let y equal r tangent theta. And actually, I should really have written that further up, so I'm going to move it now. Cut. Paste. There you go. So let y equal r tangent theta, and then that means dy is equal to r secant squared theta d theta. Not only that, if you look and try to make out what this sort of potential triangle is, you would see that the angle theta would be right here. This quantity would be r, this quantity would be y, and this quantity would be the square root of y squared plus r squared. So if you look at that, when y goes to positive infinity, theta just goes to pi over 2. And when y goes to negative infinity, theta goes to negative pi over 2. So that's something else we have already worked out in our favor. Now I'm going to substitute that stuff back in. I've got a negative mu 0. Actually, I don't think I'm going to fit that in the space, so I'm going to go ahead and put it on the next line just to keep it from getting so messy and small that you can't read it. So I'm going to say negative mu 0 I times r times k hat divided by 4 times pi times the integral of, now dy we get to just replace with r secant squared theta d theta. And now we have a r squared plus r squared tangent squared theta. And all of that down there is to the 3/2 power. So notice I now have the ability to factor out a r squared inside of those two terms inside the 3/2 power. So r squared to the 3/2 is r cubed. So that comes out and becomes r cubed, and the two r's on top become r squared, so that we end up just getting a single r in the denominator. Everybody follow that? So I'm going to write it down now. If you don't get it, this will be the perfect time for you to ask. Over 4 pi times r, and all we have left there is the k hat. So remember what I said, we had the r, and the r made r squared. We had these r squareds that made r cubed under r squared, so that left just r to the 1 in the bottom. So hopefully everybody followed that. Make sure you ask me if you didn't. Now the cool part is this denominator inside of here, after you factored out the r, it became 1 plus tangent squared theta, and the trig identity 1 plus tangent squared is equal to secant squared. So that being secant squared theta, when you raise it to the 3/2 power, you get secant cubed, and that makes it secant cubed under secant squared. So my integral is now secant squared theta over secant cubed theta d theta. And this is from theta equals negative pi over 2 to pi over 2. Okay. Now, obviously, the secant squared completely cancels out, leaving just a secant in the bottom, but 1 over secant is in fact cosine, so we just get a simple integral of cosine, and we get negative mu 0 I over 4 pi r k hat times the integral from negative pi over 2 to pi over 2 of cosine theta d theta. Now we know the derivative of sine is cosine, so the integral of cosine is sine. That means we're going to get negative mu 0 I over 2, or excuse me, over 4, predicting the results there, over 4 pi r k hat times sine of pi over 2 minus the sine of negative pi over 2. And this sine of pi over 2 did not turn out very neat looking, so I'm going to clean that up a little bit with my itty bitty eraser. Okay, now we know that the sine of pi over 2, which is of course 90, is obviously just 1. So this quantity is going to be 1. And the sine of negative pi over 2 is, if you remember, sine is actually what we call an odd function. So it would be negative 1. So this little quantity here is negative 1. So we've got 1 minus negative 1, which you know means plus a positive. So that's actually going to come out to be just 2. So my final answer is negative mu 0 I. Because the 2 was in there, that's going to cancel out with the 4 on the bottom and just leave, oh man, that's going to cancel out with the 4 on the bottom and just leave 2 pi r k hat. And that's the actual answer for the magnetic field. Notice that's exactly what I told you earlier when we first introduced the magnetic field created by a current carrying wire. We said it obeyed the right hand rule, where you put your right thumb in the direction of the current, and then your fingers curl around the wire in the same direction that the magnetic field lines do, and that makes it counterclockwise as seen from above the wire. And that counterclockwise, of course, means into the page at point P. So if this was not, strictly speaking, just in the XY plane, you would see that you could rotate that coordinate system by like a couple degrees, and it would still point into the board, and a couple more degrees still point into the board. When you do that after a complete rotation of 360 degrees about the y-axis, you eventually figure out that that's sort of the theta hat direction that we talked about in polar coordinates, only that's normally only true with the vertical axis being the z, not the y. So either way, that's it. Anybody have any questions on that one? All right, so maybe it wasn't quite as bad as I alluded to, but I think, yeah, I get it if that was a scary thing for people. But the nice thing is it happens to be the same integral that we've done a bunch of times. Now, let's use the law of Biot-Savart to do another one. I did leave a blank page because I expected I might have to go into the next page to do this, but I didn't. So the next one is use the Biot-Savart law to calculate the magnetic field at the center of a circular wire carrying a current I. Assume the wire is bent into a circle of radius r. So there's my actual current carrying wire. I'm going to assume, I didn't even list it on here, but I'm going to assume that the current is going this way in these locations. So the current, if you look down from above, the current is going in the counterclockwise direction as seen from above. So let's go ahead and get started. Again, our solution requires the law of Biot-Savart. And the law of Biot-Savart says dB is equal to mu 0 I over 4 pi times dl cross rp minus rdl over the magnitude of rp minus rdl cubed. So we've got to figure out what all those vectors are. In this case, we're kind of lucky because the point P that we're asking for is the actual origin, and the vector RP is supposed to point from the origin to P. So that should tell you what RP is. Anybody have an idea? Or anybody figured out what RP would be? Big hint, I'm writing it right here, so it must be small. It will be the zero vector. And that's because, like I said, you're supposed to draw RP is supposed to be a vector from the origin of your coordinate system to the point P at which you wish to know the magnetic field. In this case, the point P that we wish to know the magnetic field is the origin, so the vector going from the origin to the origin is a zero vector. So we've got RP. I did it in purple just because it was right next to the blue. I'll go ahead and do the other vectors in purple, and then we'll start off with blue again after that. I don't know why any of that matters, but just telling you. Now we've got RP. What we also need to do is figure out where is a piece of DL so that we can put RDL. Well, what I'm going to do for my DL is I am going to use this little bit of vector right here. And the way that's going to work for me is I am going to imagine a line in the XY plane that is at angle theta away from the positive x-axis. And then I'm going to let that angle theta increase from theta to theta plus d theta so that that little angle in there is d theta. Okay. Now, the radius of that, of course, is r. So what this tells us is that this vector right here, which is dl, that dl vector should be r times d theta. Now, what direction does it point in? I can give you the quick answer and say, oh, it's the theta hat direction, but I think it might be a little better if we don't think about it that way until you get used to thinking what theta hat is. So I'm just going to treat it like it's a vector that we got to figure out. So if I look from above, what I would see is the green line I had, right, or excuse me, I was going to say the green line and I ended up writing in purple. The green line that I had, and then the other green line that I had, something like that. The purple vector that I had went from here to here. And what we know is this angle right here is theta. And of course, this line that I just continued in purple, but now I'm putting sort of green dots, that one is a radial line. It actually is parallel to the green line that went from the origin to it. Now I'm going to draw my x coordinates, my x-axis on here. And the x-axis is, of course, right to the right. And I'm going to put my y-axis right here as well. And that just points up. Notice I just took, or excuse me, that's my z-axis. Shouldn't say it that way. Oh, no, that is my y-axis. And yeah, that is my y-axis. Sorry. That is my y-axis. I've turned it sort of 90 degrees from what you're seeing, but hopefully that's not causing any problems. Can everybody understand what this drawing is? It's supposed to be this little quadrant right here drawn as if our eyes are looking down like that. Does that make sense to everyone?
Yeah.
Okay. Sorry if it's a little convoluted. So the reason why I drew that radial line outward is because I know that radial line is at an angle of theta. So this angle right here is theta. That means this angle right here is also theta. Now, because of that, I can say that my components of that little DL vector, which is what that purple thing is, let me write it over here to label it. So this is my DL vector. You can imagine, if we look at this closely, you can imagine that the X component is this way, and I think you can see that that would be negative DL times the sine of theta. But you can also see that the y component is this guy right here, and that would be dl cosine theta. So that's what our vector is. I'm going to now write that out as dl, which has a magnitude of r times d theta. So when I was saying dl times sine theta or dl times cosine theta, I actually said dl times the negative of sine theta. That's what I mean. It's just r times d theta. So now I'm going to multiply this magnitude r d theta times negative sine theta to get the x component. So it'll be negative sine theta I hat, and then positive cosine theta j hat for the y component. So now I have the very vector that is dl. And you can see in this case, when we go to do the cross product, we actually have to do the true FOIL method because we're going to have two binomials that we have to multiply. So I've now got vector RP. I've now got vector DL. I now need vector RDL. And that's the vector that points from the origin to the tail of the vector DL. So I need RDL. And I think you can see a little bit what it's like because RDL is actually in this diagram, RDL would be this vector coming all the way back from the origin. So it really is that one. You can tell that that's at an angle theta, and you can probably even tell that the x component is going to be cosine theta, and the y component is going to be sine theta. So I'm going to go ahead. Well, I'll just leave that r, or excuse me, that little red vector there to represent, as I said, that's r dl, even though I've now written it so small that we won't see it when I shrink it back down. All right. Now that I have that, I can go ahead and say RDL. Its magnitude, of course, is R, whereas the other one was RD theta. The magnitude here is just R, so I'm going to put the R out in front, and then I'm going to multiply that by cosine theta to get the X component, and I'm going to multiply that by sine theta to get the Y component. Okay, so if you look back at this diagram again, remember capital R times cosine theta is the x component, and capital R times sine theta is the y component, because this is a vector whose length is r and is the RDL vector. Any questions on that one? So being methodical like this really, really helps to get through these complicated calculations. So I definitely recommend you paying attention to that as much as you can. Uh, what I'm now going to do is go ahead and take the time to do the cross product while I've got, quote unquote, a lot of room. So I'm going to do the cross product, and the cross product is DL cross RP minus RDL. The DL, of course, is just R d theta times negative sine theta I hat plus cosine theta j hat. And then that's going to be crossed with RP minus RDL. We already know RP is 0, so when I subtract RDL from it, I get minus R cosine theta I hat minus R sine theta j hat, like that. Obviously, that would be beneficial to go ahead and include those R's and stuff with the negatives. So I'm going to write it as negative R d theta sine theta I hat plus R d theta cosine theta j hat. That's going to be crossed with negative R cosine theta I hat minus R sine theta j hat, which seems like a lot of algebra, but luckily remember I hats cross I hats, j hats cross j hats, and k hats cross k hats always give us 0. So I'm going to do my FOIL method, my first, and then my outer, and then my inner, and then my lasts, like that. We'll continue on as follows. Remember what we do with our scalars is we pull them all out in front. So the very first thing I'm doing is the first term times the first term, and I get negative times a negative r squared d theta times sine theta cosine theta, and then times I hat cross I hat. That one's obviously going to be 0, because the cross product of any parallel or anti-parallel vectors is 0. Now I've got to do the outers. So that's the first and the last, for instance. And the outers give me negative r d theta times negative r. So that's going to be plus r squared d theta. And this time it's sine squared theta. Or Matt keeps getting kicked out for some reason and has to come back. That's r squared d theta sine squared theta. And then this one is I hat cross j hat. So that's I hat cross j hat, which will work out. Now I'm going to do the inners, which is the second times the first. So I'm going to say, in this case, I notice it starts off as negative times a positive. So I'm going to put a negative here instead of subtraction. It really is addition, but I would just want to go ahead and make it a negative because of the negative sign. I again get r squared d theta, and this time it is cosine squared theta. And then it's j hat cross I hat, which is the opposite of I hat cross j hat. And by the way, when you do A cross B, B cross A is the negative of that. So that's another good trick to help you when dealing with these. Now all we have to do is the lasts, and that's the second term times the second term. But you can see that is going to be a j hat cross j hat. So that's going to be a 0 as well. I'm going to write it down here, just stagger it a little bit, just so we can see it without me fitting it in. Notice it does have a negative, so I'm going to say minus r squared d theta. Because there's an r in each of them. There's a negative r in the negative r sine theta j hat, and there's a d theta in one of them, and then it's sine theta cosine theta. And then this is j hat cross j hat. So that's our FOIL method. And this vector again is 0. And if you draw a right-handed coordinate system, you can see that this is x, this is y, this is z. So I hat cross j hat means take your index finger, this one right here, and point it in the x direction, which is out of the page. Take your middle finger and point it in the y direction, which means it's to the left. And now you see that the thumb is pointing up, which is the k hat direction. So I hat cross j hat is k hat. And j hat cross I hat, therefore, is negative k hat, which is nice because that negative k hat with this negative sign makes it positive. So now my cross product can be written as r squared d theta sine squared theta. That's the k hat one. And then minus r squared d theta cosine squared theta negative k hat. So that's what I was talking about, the two negatives working out. So now we finally have the answer of the cross products, which is r squared d theta times sine squared theta plus cosine squared theta times k hat, and of course r squared, or sine squared plus cosine squared is just equal to 1. So our final answer for the cross product is just r squared d theta k hat. So now we're free to compute the rest of the integral. And the way we're going to do that is as follows. We have b is equal to mu 0 I over 4 pi integral dl. Now we said our dl was, actually, no, we've already done dl cross rp minus rdl. So we're just going to write r squared d theta k hat. I got ready to recalculate all that stuff for a second there. That would not be good. Now I'm going to divide that by the magnitude of rp minus rdl. If you look at rp minus rdl, that is 0 minus r cosine theta minus r sine theta. Obviously, the length of that vector is the same as the length of RDL, which is just r. So down in the bottom here, I'm just going to put r cubed. Everybody follow that? Anybody have any questions on that one? All right. So I'm going to move along. R squared here, that whole r squared cancels out and leaves just a r1 down there, r to the 1 power down there. So I can just pull that r to the 1 power out in front, and in so doing, I'm going to get mu 0 I. I'm going to go ahead and put the k hat out in front too, divided by 4 pi r is equal to the integral from of d theta from theta equals 0 all the way to 2 pi. So you can see that if this circle would have been less than 2 pi, we might have got a different angle. I mean, a different result, but it would still look exactly the same. Instead of me multiplying by 2 pi in the numerator, if it was, for instance, a quarter of a circle, it would be pi over 2. And then that pi over 2 would be in the numerator with the mu 0 I and the 4 pi r in the bottom. That's pointing to where we're going. So now that I've computed this, we know that the integral of d theta is theta, and taking the limits of integration, that means 2 pi minus 0. So the result is going to be 2 pi. For this particular integral, the result is just 2 pi. And that means we're going to get mu 0 I over 2r. So it'll be mu 0 I over 2r k hat is the magnetic field at the center. And that is consistent with our right-hand rule. Notice if you grab the wire, let's say right there on the part of the wire that's on the positive x-axis, if you grab that with your right thumb pointing to the right, which is the direction of the current, and you're imagining going under that wire so that your so that your fingers can curl up through the middle, you'll see your fingers are coming up in the middle. That means the magnetic field at the middle, as a result of that little bit of current, should be upward. And that's exactly what we got. And in fact, that's a big thing that we can use, because what we found was B is equal to mu 0 I over 2R. And this one's going to be K hat, but that's for a full circle. So if, for instance, if it wasn't a full circle, let's say, for instance, it was a half circle like this, then it would have been mu 0 I over 4 pi r times, in this case, it'd just be pi. So you'd get mu 0 I over 4r. So you can sort of think of the magnetic field of a arc at the center of the arc now. That magnetic field strength is going to be mu 0 I over 4 pi r times whatever the angle is, which you might call delta theta or you might call it theta. And then it's just a matter of using your right hand rule to figure out whether it's in the page, out of the page, to the left, to the right, to the up or down or whatever. So that's just going forward something that we can use, and our answer is here. Anybody have any questions on that one?
Nope.
Okay, so I said we're pointing to something that's coming in the future. Here's the future. Okay, these are supposed to be circles, or parts of circles, but the program was able to draw it fairly neatly, but not good enough. So, anyways, we're going to ignore it. But what we have here is a current we could imagine starts here. It's going to the right along a line that points right to the origin, by the way. So that means something. Then it's going to hang a left and make a quarter circle of radius R0. Then it's going to make a left, make a quarter circle of capital R0 radius, take a left, and now it's going to make a quarter, or actually a whole half circle of radius R1 all the way around like this. And what I'm saying is what we just learned is enough to tell us exactly what this answer is. So what we discovered was using the solution. We could use the law of Biot-Savart, and we are using the law of Biot-Savart, which I'll write again as GB is equal to mu 0 I over 4 pi times dl cross RP minus RDL divided by RP minus RDL magnitude cubed. So that's it. But the result we got for any circle was mu 0 I over 4 pi r times delta theta, where delta theta is the angle through which the arc turns. Okay. So what I can do is I can imagine grabbing the wire, specifically this particular wire. If I imagine grabbing it right here with my right hand and my thumb pointing this way, like that, then I see that the magnetic field due to that piece of wire is going into the page. I remember we are actually calculating it at the origin. So this is the point P, but the magnetic field due to this guy goes into the page. What about this guy? Can anybody tell me what direction the magnetic field goes at the origin for that particular wire?
It's going to go out of the page to the right
Okay.
because your thumb.
So yeah, notice the current is going down and to the right here. So you want to grab it with your right hand, and that means you want to put your thumb this way, and here's your knuckles this way. And notice your palm is actually facing into the page. So you want to reconsider which direction that is?
Into the page.
Into the page. Very good. So that one's into the page. Now, can anybody tell me what direction this hoop is going to cause the magnetic field to be?
Be into the page as well. Palm will be down.
This one's going the opposite way. So now if I put my thumb here, ooh, I'm actually drawing instead of using my laser pointer. You want to change your answer now, Josh?
Yeah, I think we know what the answer is now.
Yeah, exactly. So that one's out of the board. So what we'll do is notice the way this x-axis is drawn to the right and the y-axis is drawn up. That means our z-axis is pointing out of the board. So what we'll do is we'll say the big arc is a positive magnetic field and the two small arcs are negative magnetic fields because they're all going to point in the plus or minus k hat direction. So what I'll do is I will label these as segment 1, 2, 3, 4, and 5. And I'm going to say segment 1. I'm making this argument and I'll prove it in a second, but segment 1 implies B equals 0. Okay. I can tell
Do you
you
need an
why.
additional segment between small r 0 and
Oh,
big R
yeah, I
0?
did. Thank you. Look at
Yeah,
me missing all
just checking.
stuff. Yeah, I appreciate that. That would actually be good. It's much better that you catch that. Okay, so I've got the 2. Yes, I completely forgot that guy. So this little guy will be 3, and this one will be 4, and this one will be 5, and then this big one will be 6. Okay. So yes, as we said, part 1, you can see that DL, I'll go ahead and do the explanation now. DL is going to be, make sure y'all can agree with me on this. DL is going to be DX I hat. RP is going to be 0, and RP minus RDL is going to be negative, let's call the distance X I hat, because the RDL vector will be pointing from here to here. So can you tell me what's going to happen when I take the cross product of DL, which is DXI hat, and RP minus RDL?
Zero, right?
Exactly. So that's why it comes out 0, and that is DL cross RP minus RDL equals 0. And that's true for any of those line segments that are pointing right towards or right away from the origin. Okay, which is the point, is the point here. It's pointing from the to the origin, the point P. So with that in mind, we've got 1. Now segment 2, we found that one was going to be into the board, which is negative k hat direction, and I'm going to say delta theta is going to be pi over 2. And then number 3, I'm going to say that one is DL cross RP minus RDL is equal to 0. So B is equal to 0 for that one. How about 4? Can anybody remember what the direction will be now? It was negative k hat again. And what about the change in the arc? We're going from this line to this line. How many delta theta radians is that?
That's pi over 2.
Very good. And we've got 5, which I'm just going to say B equals 0 for obvious reasons. And then we've got 6. Now, it probably wouldn't have hurt for me to put the radii with each of these two in retrospect, but that's okay. We'll remember it as we go. But for 6, we found out that it's going to be the positive k hat direction, and now the delta theta is actually going to be a whole pi instead of pi over 2. So does that make sense to everybody, what I just wrote?
Yeah.
All right, so now what that tells us is we know the formula for the magnetic field. Basically, the total magnetic field is going to be the sum of all those parts, which is going to be 0 for part 1. And then for part 2, it's going to be a negative mu 0 I over 4 pi. Now, the radius of that guy was little r 0, so it's going to be that, and the negative was the k hat direction. But now we got to multiply it by delta theta, which is going to be pi over 2. I should have put the pi over 2 before the k, but it doesn't matter. It's still correct. Now part 3 is going to be 0. Part 4 is going to be again a negative. That's going to be mu 0 I over 4 pi. This time it's a big R0, and the angle is pi over 2, so I'm going to remember to put it before k this time. And now I'm going to put the k hat there. So now I've done 1, 2, 3, and 4. 5 is a 0 again, so I'm going to say plus 0. And then 6 is going to give us a positive mu 0 I over 4 pi. This time the R is called R1, and the angle is actually pi, and then k hat. So our B total is going to be equal to, we see a common factor of mu 0. Whoa, Nene. Probably should write with a pen instead of a laser pointer. We see a common factor of mu 0 I over. I would want to put pi, but notice the pi cancels out in every case. So what I'm going to do is just, yeah, I'll put the 4 down here and see what happens. So I'll just put the 4 down here and leave the pi. And then what we're going to have is, in this case, it's pi over 2 lowercase r0 k hat. And the next case, oh, that's a negative 2, by the way. And then the next case is going to be negative pi. Oop, I already got rid of the pi, so the pi shouldn't be there. Sorry, I'm trying to do something on the fly here and thinking my way through it. We already took care of the pi. Well, let's not skip steps. It'll be better if I didn't skip steps anyway. So I'll put the pi here for right now, and then we'll work it out. This is going to be negative pi over 2 r0 k hat. The next one's going to be negative pi over 2 big R0 k hat. And then the next one's going to be plus pi over R1 k hat. So now we can simplify a little bit more. We can see, as I said, the common factor of pi that cancels out. We can also see that we're going to get, in the first case, mu 0 I over 8 R0. All of these are going to have a k hat, so I'm going to write them this way and leave the k hat at the end as if it's factored out. So I'll put a square bracket around that. And then the next one's also going to be a minus, and it's going to be the same thing as this one, except a different R. So it's mu 0 over 8 times big R0. And then the next one's going to be a plus, and it's going to be mu 0 I. In this case, the 4 doesn't change, so we have the 4 times R1, and then all of this in the k hat direction. That's about as good an answer as any. Maybe I'll write it one more time for cleanliness as negative mu 0. Actually, let's put it in a different order. I'll say mu 0 I over 4 R1 minus mu 0 I over 8 R1 or R0 minus mu 0 I over 8 lowercase r0, all of that times k hat. And that's the way you do that. So that is really like the nastiest type of problem to sort of work out the details of. But once you do it one time, you can see this little pattern and you can use that repeatedly. So you're, in some sense, you're using the law of Biot-Savart, but in another sense, you're just completely avoiding it and using the concepts that you learned more. So does everybody understand that?
Yeah.
Anybody
Yeah.
have any questions? Something that bothers you about it or anything? Okay.
I'm good.
Good deal. We'll move along. And now what I want to show you is now that we've done the law of Biot-Savart, notice I'm doing this the opposite of your textbook. Your textbook, Giancoli, does the Ampere's law first, and then it does the law of Biot-Savart. That's weird. All of a sudden, a blue pin mark came up on my book. I don't
Yeah,
know.
sorry, that was me.
Okay,
I bumped the screen. Apparently,
you've got superpowers.
I can edit your, or I can like draw over your notes apparently.
Evidently. Could you mind erasing that blue thing
No,
for me?
yeah, I
Okay.
hit the delete.
All right. So here's Ampere's law, everybody. I'm gonna write Coulomb, or excuse me, Gauss's law first, just so you'll have a recollection of what that is, so you can see the differences. But Coulomb's, or excuse me, Gauss's law was the closed integral of E dot dA is equal to Q enclosed over epsilon naught. Ampere's law, however, is the closed integral of B dot, notice this part, dl. So this is a contour or path or line integral over a closed contour path or line. And the other side is equal to not 1 over epsilon 0, but mu 0, and then times I enclosed. And there is sort of a sign convention associated with this. The current I is considered to be a positive if you integrate in such a way that you integrate around the loop, and if you curl your fingers around the loop in this of your right hand, curl your fingers of your right hand around the loop in the same direction that you integrate. If your thumb is of your right hand is pointing in the same direction of the current, then the current will be positive. Otherwise, if it's pointing the opposite way, the current will be negative. So that's sort of a big deal. Now, we already know, for instance, that a long current carrying wire has a magnetic field created by the current of mu 0 I over 2 pi r. So we can make use of that. In fact, I'm going to try to move both of these over a little bit. I can make use of that. Crap. I can get rid of this. There you go. Now I'm trying to move this wire back over to there. So this is our long current carrying wire, just like the one we just did with Biot-Savart law. But now I'm going to do it with basically Ampere's law as sort of the kindergarten version of Ampere's law, even though it's full force Ampere's law. Okay, this is my y-axis. This is my x-axis. And then up along the wire going in the direction of the current is the z-axis. This is my current that way, uh, going that direction. Now, what I know is from my experience with the law of Biot-Savart, I suspect that if I were to grab that wire with my right hand and point my thumb in the direction of the current, then look down on the wire, my fingers would be curling around it in a counterclockwise way. So I have to make a hypothesis about the actual actual magnetic field. So here's my hypothesis. And by the way, I have started solving this or deriving it. So I went ahead and wrote the word solution. I could have wrote derive or something like that. But what we're going to do now is we're going to use that hypothesis just like we do with Gauss's law. Our hypothesis is that B is equal to B, a function of R only, where R is the radial distance in the XY plane. So even if we're measuring up high above the XY plane, I'll still draw a line that's parallel to the XY plane radially out to that point, and that would be the distance R. So I'm saying B of R, and its direction would be what I would normally call the theta hat direction, which means basically when when theta is 0, it would point this direction. When theta is 90 degrees, it would point this direction. When theta is 180 degrees, it would point this direction. And when theta is 270 degrees, it would point this direction. So that's what the theta hat is. Now I'm going to draw a plane on this wire that is perpendicular to the wire itself so that you can get a feel for exactly what direction the magnetic field points at various locations. And you'll see that they actually match exactly the theta hat direction. So according to the right-hand rule, what we get is an oval. You can imagine a circle whose radius uh, is r, basically. If you fix that r, then the magnetic field strength will be the same everywhere on it. So this one's going to come right around here, about there, say, and then that way. So that's the circle of radius r in that perpendicular plane, that plane that's perpendicular to the wire itself. And what this means is, because it's going counterclockwise, this means the magnetic field points around counterclockwise. And at very specific locations, that means the magnetic field points this way in front of the wire, this way to the right of the wire, this way behind the wire, and this way to the left of the wire. And of course, between it would also be like this as well. So you can see that that really is exactly the theta hat direction. But now that we have that hypothesis, we can write left-hand side of Ampere's law, and we're going to say the closed integral of B dot dl is equal to the integral of B of r theta hat dotted with, and now I think you'll recall we've done enough of these little differential area elements, or differential length elements along an arc, for you to recognize that the dl for this guy is dl is equal to r d theta theta hat, like we've done like 1,000 times. So that's what we're going to use now as our differential line element. So that's r d theta theta hat. Again, the dot product is a linear operator, so I can pull out all the scalars in front, and I'll get b of r times d theta, and then all I have left is theta hat dot theta hat. And this one cracks me up because it looks like a drunk owl. So in this case, I'm going to say theta hat dot theta hat is just 1. So we got nothing to do there. And not only that, since we're on a circle of radius r, the b of r and r come out in front because they're constants, and we just get the integral d theta from theta equals 0 to 2 pi. So we get 2 pi r times b of r. And that's the result, but it's also a pattern. Remember last time when we were talking, or I shouldn't say last time, but back when we were doing Gauss's law, I told you the left-hand side always becomes E times some area, or maybe E times an area plus E times an area plus 0, or E times an area plus 0 plus E times an area, or something like that. Well, the left-hand side of Ampere's law always becomes B times a length. In this case, it's 2 pi r. Let me go ahead and quickly do, because we're actually a minute over. Now I'm going to do the right-hand side. The right-hand side is mu 0 I enclosed. You can see that the current I, when I lay my right fingers around that circle in the direction of those red arrows, my right thumb points in the same direction of the current. So that means the current is a positive. So I can just write mu 0 I. Now I set left-hand side equal to right-hand side, like we did with Gauss's law as well, and I get 2 pi r b of r is equal to mu 0 I, and therefore, using our hypothesis, we say b is equal to mu 0 I over 2 pi r in the theta hat direction, and that's it. You guys are free to go. Like I said, I will be posting some more videos. I'm waiting for the last person to leave in case anybody has any questions, but you're free to go. Thanks for coming. Thanks for sticking around. And like I said, I'll wait here if anybody has anything.
All right. Have a good night. Thank you.
You're welcome, guys. And ma'am. Jen, did you have a question?
Yeah, is this the last lecture?
This is the last one that's official lecture. I'm going to be showing up for the other ones, just in case y'all have any questions. So there'll be like free office hours. But yeah, we're not doing any more. But I am doing a couple videos
Okay.
to augment the material between now and Sunday.
Okay, well, I'll watch out for those then.
No problem. Yeah, keep an eye on it. And like I was telling them, I think you might not have been here, but you'll see it if you watch the beginning of the video. Uh, I'm trying to do, this is more or less chapter 28, and we're starting into 29 even, but I'm trying to do 28, 29, and 30. If I look and it looks like all you guys are really taking this seriously and watching the videos, not just watching 2 minutes of them when I send them out, and maybe even doing the homework for those chapters, I might completely leave 28, 29, and 30, or at least 29 and 30 completely off the final. So
Okay.
I want y'all to learn it, but I don't want to harm you by it because, my course ran longer than it's supposed to. So just pay attention as best you can.
Will do.
All right. Have a good one, Jim.
Okay. Thank you.
You're welcome.
Bye.
Bye-bye. All right. So that's about it. See you, folks. Just looking at my minion.